All right, so today, as promised, we're going to kind of formalize this a little bit and talk about the definition of the limit of a function and talk a little bit more about ways that we can find these without just plugging in closer and closer and closer values and then estimating what it comes up to. But first, a formal definition, just because it's in the book, it's highlighted, it's in a box, it must be important, right? So I should probably write it down. So this is what we've been working on. This is the notation. What is the cursive L thing?
What are the X?
Oh, okay, so this is shorthand for limit, L-I-M. Okay, that's the point on.
No, I knew that.
Limit, lim, come on. So, and then this is the number that X is approaching. So in the last problem we were approaching 1, right? Because we kept picking closer and closer values to 1. This is the function that we're interested in. So in the last problem that was sine of 10 pi over x. And this is the answer that we come up with. Okay? So that's the formal way that you write that whole thing out. And it doesn't always exist. For this to work out, you need to be able to get, basically closer and closer to this, as close as you want to this. So if it's bouncing around all over the place, there's cases where it doesn't exist, and we'll talk about those as they come up. But the key here for us is that that's the limit as x approaches that number a. It doesn't have to be when x equals that number. It's as it gets closer and closer to it. So for example, you got that? Yeah? Let's take a look at the limit as x approaches 1 of x minus 1 over x squared minus 1. And so now we're not doing the whole slope thing. We're just trying to figure out what value is the function getting closer and closer to as x approaches 1. Okay? So let's put this in the calculator again. So x minus 1 over x squared minus 1. Don't forget, if you're doing this, you have to, since you've got 2 terms on the top and 2 terms on the bottom, you have to use parentheses, or else the calculator will give you a different graph than what you wanted. Was it x squared minus 1 on the bottom? Okay, so I'm going to type that in there, and then I'm going to go back so that my table is automatic. We want the limit as x approaches 1, right? Nod your head and smile. Okay. Smile and wave, boys. So I'm going to start my table at 1. And then I want to get really close to that, so let's go by 0.01 each time. Okay, and so now we have it set up. So we're starting at 1. We're going by a very small amount, and it's going to automatically give us all the values that we want. And so I'm going to scroll up just a little bit so I can see numbers on both sides. As I'm approaching 1 from smaller, bless you, numbers, what are these getting closer and closer to? 0.5. As I'm approaching from bigger ones, what are they getting closer and closer to? 0.5. Okay. Why is there an error right at 1? If you think about the original function, why did we get an error there? Mumble, mumble, what? Yeah, because you can't divide by 0. So I can't plug 1 in here and get an answer because 1 minus 1 is 0. And so I actually get 0 over 0, and so I can't figure that out. But if I look at the table there, we're able to guess that this answer is 0.5. Okay? So if you were asked that problem, that's the answer. That's how you do it. A lot easier than the whole figure out the thing and figure out the slope knowledge. Does that make sense? Okay? And so, like I said, it's important to understand that we're talking about as it approaches 1. It doesn't matter that it doesn't equal that at 1. We just want to get as close as we can from either side. That's why it's called a limit. All right? Okay, so since we figured this out, well, let's look at the graph first. So let's go back and look at the graph. That was zoomed in quite a bit, huh? Okay, so there is the graph of the function. What is happening right here at x equals 1 that our calculator does not show? There's a discontinuity. Excellent. Okay, there's a little hole right there. Okay, because when x equals 1, the answer is undefined. Okay, so there's a really tiny hole. How big is that hole?
Can't even see it.
Can't even see it. It's an infinitely small little hole because we could get as close to the graph touching as we wanted to, but they actually never will. So technically there's a little hole right there. And so what we could do, now that we know the limit of that function, is we could redefine our function with a piecewise function and fill that hole. Okay, and so the way you guys have seen the piecewise functions before, right? So our original function looks like this, but where does the problem occur with that original function? At x equals 0, or x equals 1, sorry. Okay, so we have to say x can't equal 1 when we're doing that. Okay, what would we like that function to equal when x does equal 1? 0.5. And if we set it up like that, now we have filled the hole and we have taken what was a discontinuous function and turned it into a continuous function. Okay, with that one little simple trick. Okay? Okay, the book says we could have been wacky if we wanted to, and instead defined this to be equal to, you don't have to write this down, just for funnies, we could have made that equal to 2. Okay? And if we had made that equal to 2, then the graph would look like this, and then where x equals 1, there would be a little dot right there at y equals 2. Okay? So it's like where the city workers, there was a hole in the road, and we filled the hole in the wrong place. And then they went home and said, you know, we did what we were supposed to do, don't worry about it. Okay, but it makes more sense to define it so that it equals the limit. All right, so will you do this on your own?
That's what it is. Should I give where
See what you can come up with for that on your. Yeah, the answer equals 1/6. Okay, so you should notice that these are getting closer and closer to 0.16 repeating, which everybody knows is the common fraction of 1/6, right? Okay. Okay, so that's all we got going there. So that's quite a bit easier. Now they want us to notice something about these calculators. Let me catch up to you real quick. So square root of, what was it? X squared plus whatever. Thank you. Divided by x squared. Okay, so if you go back to the table, we can start at 0. Okay, so instead of going by 0.01s, I'm going to change mine so that we go by 0.0001s. And now if we look at the table, oh, never mind. Okay, you're good. Must be an old book. because we're supposed to get totally different numbers for things very close to zero. It says in red, calculator gave false values, but they've, the wonderful people at Texas Instruments have fixed that. All right?
Get it?
Okay, I think you guys are good. Yeah, I think I'm gonna turn you loose. Do some of these on your own.
Yeah, look at it.